Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Joe Hahn with us today. Hello, Joe.
Hello, I'm delighted to be here. Thank you.
Well, thank you for agreeing to talk about your very awesome article, which we'll get to here very shortly. And Joe, what is your geolocation?
I am in Cedar
Hey.
Park, Texas, near Austin, Texas, very close to all that flooding we've been hearing about on the news.
Yeah. So, it's raining in Texas in the summer,
We
or
had
at
a lot of
least
rain, and fortunately, I'm on the high ground, so me, my neighborhood, my family, friends, we're all good. But there
good.
was a lot of destruction, and quite a few people got swept away.
Yes, it is not a nice scene. And it is July 8th of 2025, and I'm in Phoenix as we record this, and we are definitely in our summer months. We are hitting the 110s, Fs, or the 40 Cs, somewhere in there. So yeah, nice and toasty as we go on through. So okay. And Joe, what do you like to do for research?
Oh, I'm planetary dynamics is my thing. So
Cool.
early on, I started out with planet formation, got into origin of the Kuiper Belt.
Cool.
But all along, I'd be going to conferences and hearing all these interesting talks about planetary rings.
Mhm.
So I was slowly evolving into planetary ring studies, and that's where I've been for quite a few years.
Yeah. Then we get banging on this one.
Mhm.
Awesome. And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one.
It's not free yet. I haven't paid for it, but that's on my
Ah!
agenda. It's free for readers right now, but I still got to change it up to page charges.
Oh, you caught me on that one. Okay. Well, you're going to pay
I'm
those
working
page
on it.
charges, article charges. Okay, here we go. N-body simulations of the self-confinement of viscous, self-gravitating, narrow, eccentric planetary ringlets. And Joe, take us away.
That is a mouthful, right?
It is. There's lots of things going on in there.
Should we talk about planetary ringlets, or should we get to my co-authors?
Hmm. Indeed.
Oh, so let's see. Doug Hamilton, old friend of mine. I'm very pleased to be working with him on this one.
Nice.
Thomas was Doug's grad student when this project started, so he's
Oh,
since
wow.
graduated. He's out in the field as a new PhD.
Cool.
And Lucy was Doug's intern. Again, this was years ago we first started this, so she, I
Ah,
believe, is a grad student, possibly graduated by now.
yeah. Okay. Awesome. Great crew. Good shout out. Okay. Let's get into it.
Narrow eccentric planetary ringlets. That's a mouthful. So we're familiar with the broad rings at Saturn,
Yeah.
right?
Yeah.
The
Big
two
ones.
big broad ones, but they have a few narrow ones.
Uh-huh.
Uranus has several narrow ones. And what's of great interest to me is they're narrow and they stay narrow over time,
Yes.
which is a bit counterintuitive because planetary rings are composed of mostly small chunks of ice. They're all traveling in Keplerian orbits, so the
Mhm.
ones closer to the central planet are moving faster. So
Yes.
they're nudging the ones exterior, and meanwhile, the ones exterior are moving slower. So what happens is all those nudgings, the friction associated with that, causes angular momentum to spread radially. It always goes outwards. I say
Yes.
almost radial, almost
Yes.
always.
Hmm.
So if you're in the inner edge of the ring, and you're losing angular momentum, it's going out, you want to go inwards. And
Right.
likewise, if you're the outer edge, you're acquiring angular momentum. The natural inclination of the ring is to spread radially, and yet they have sharp edges and they're confined for long periods of time. Why do they have sharp edges? What's the confinement mechanism? That's been
Shepherds
top of
is
mind for me for decades.
Shepherds has
Uh,
always been, the
exactly.
commonly said thing for those. Yeah.
So Shepherd satellites was the prevailing theory again for decades. And
Hmm.
I was always a bit suspicious because we know when you have a moonlet orbiting near a ring, what it does to the ring, it perturbs the ring. So even if the shepherd is so small that you can't see it,
Okay.
it tends to make a big disturbance that is very, very easily detected.
Yes.
Um, and so Cassini went to Saturn, and one of its goals was to find those unseen shepherds, and it saw none. So again, still top of mind. What's the process?
Okay.
Um, and the clue I thought to the explanation is one of those papers you highlighted here by Nicole. She has a series of papers She had a name change during career, so the community refers to her as Nicole. So it's N Borderies in the 82 paper, but she has
Okay.
many papers on this topic. And the mechanism is, I'm drawing a blank on here. We'll come to it. It's in here somewhere. Um, Gosh, I'm drawing a blank on her name for it. Angular momentum flux reversal, another mouthful.
Ooh, wow. That is
And
awful.
we can dive into what that means in a little bit. But I always thought that was the answer here. And
Okay.
after I work this problem some more, I feel like this is the answer. It's actually ringlets can be self-confining. Essentially, they self-excite in a way that causes their eccentricity gradient to grow. What
Okay.
that means is the outer edge gets more eccentric than the inner edge. And Nicole showed again decades ago, if that eccentricity gets high enough, you reverse the angular momentum flow. It travels towards the center of the ring instead of to the edges.
You must
And when that
cross
happens,
some threshold, right? To get
there is a threshold. There's a
okay.
magic number, and she derives it back in the 80s. And I use N-body simulations to work this problem,
Okay.
and my results are very consistent with what she reported decades ago.
All
So
right.
you
Beautiful.
hit that magic threshold, you get the angular momentum flux reversal, and everything gets more concentrated, and that's what gives you the sharp edges, I think.
Very cool. Very nice. Okay. Okay. Epi-light.
Epi and light. So this is the code I wrote to tackle this problem. And it's called Epi Light because it's the child code, the successor to a code I wrote again decades ago.
Okay.
That one was called Epi Int, and myself, and you see the reference there, Joe Spitali. We were
Yep.
using that code to essentially simulate what he sees in the Cassini observations of those main rings, the A and B rings.
Okay.
So that code was written in IDL.
Ooh,
Uh,
wow. Okay.
I've had a career change, so I no longer write IDL code anymore. I write Python. So
Python. Right.
I wrote the successor code Epi Light in Python, but its parent is the Epi code we apply to the edges of the A and B rings.
Okay. Otherwise, and shout out for open source. I'm always a big fan of open source, so you can go grab it right there and give it a whirl. Check it
Yep,
out. Do
both
so.
codes are there. So if there's interest, pull it down, play with it. When you hit issues, just shoot me an email.
Awesome. Excellent. Okay.
What else should we talk about? There's the code. Streamlines. So
Yes.
Epient and Epient Light, they're not typical N-body integrators.
Okay.
I'm interested in broad structures that are very hard to simulate in a simple N-body code. I should point out that was challenging, 10 plus years ago when I wrote these codes. I'm going to conferences now and seeing people giving, papers on 360-degree simulations of rings. So
Oh,
what was
cool.
challenging for me a decade or two ago, the technology has advanced enough. Parallel computations on GPUs means you can
For
actually do these
example.
simulations with millions and many more particles, simulate all 360 degrees.
Very cool.
I didn't have that ability. I don't have that compute power at my fingertips. I just have my 10-year-old laptop that we're communicating through. Um,
Okay.
so I use some approximations that allow me to simulate all 360 degrees of the ring,
Okay.
but not using millions of particles. I'm
Mm-hmm.
actually using hundreds or at most 1,000 or so particles.
There we
And the
go.
way I do that is I split up the ring into streamlines. Think of nested hoops. They
Mm-hmm.
all have gravity. I track the shape of the streamline through maybe 100 particles per streamline,
Okay.
tens or hundreds of streamlines. Most of my simulations, this paper only had two streamlines,
Okay.
and that was mostly
Um,
so I can compare the numerical work to what Nicole had reported again decades ago in her very important analytic studies.
Cool.
And my numerical results using the streamline approach line up with hers very close. I'm very pleased with the good agreement.
That is lovely. Okay. All right. So we're doing streamlines and let's see.
So
So,
most of the equations you see here are really about how to, generate the desired properties of those streamlines. The linear density, which often shows up in that lambda symbol you saw, and
uh-huh.
surface density. And of course, if you know where the mass is and how everything's moving, that means you can compute the gravity that all these streamline segments exert on each other. Self-gravity plays a very big role in the evolution of rings, whether it's disturbed by a satellite or if it's confined by shepherd satellites
Right.
or if they're self-confining here. So gravity is the most important force. That's the self-gravity of the ring
It's
that
gonna, it's gonna
allows the
counteract the viscosity.
eccentricity gradient to grow, and
Yes.
then you get the self-confinement state.
Cool. Yeah.
But
It's gonna
we'll
counteract
dive
the
into that,
spreading of the viscosity somewhat. Hmm.
which is important too. So real rings are composed of discrete particles. Like I said, they're bumping into each other.
Okay.
You get that angular momentum flux that is typically radially outwards. Rings want to spread because of that, because of collisions,
Uh-huh.
which we model as viscosity in the smooth sea of particles.
I'm with you.
So self-gravity and viscosity play a big role here. And most of the equations you see here are just how I handle that numerically.
Very cool. Okay. Do. And here's our flux. Yep, sure. Okay. All right. I'm good.
So I
Figure
think
one.
the figure that's coming up is
Streamline.
first results for what I call the nominal ringlet model.
Okay.
It has some particular mass, initial radial width, has zero initial eccentricity gradient, and the
Okay.
detail, the exact values are in the paper somewhere, but this is a very generic result. I've done many, many such simulations. In this case, we're doing two streamlines. They're self-gravitating, they have viscosity. So ordinarily, I want to spread over time. But what I
Hmm.
find, because the ringlet has gravity, uh, you know, the inner edge excites the eccentricity of the outer edge. As long as the ringlet has a non-zero initial eccentricity, this is very important,
Okay.
the outer edge tends to grow
Rose.
eccentricity at the expense of the inner, and that's what drives up the eccentricity gradient. And then when you hit that magic value, we'll see it later in the paper that Nicole derived again 30 plus years ago. That that so while that's happening, the eccentricity gradient grows, the ringlet spreads radially. That's what these the blue and green curve are showing.
Uh-huh.
Uh,
Outer and inner.
Same major axis of the outer edge and the inner edge. They're moving away from each other, but then it plateaus. The spreading stops.
Hmm. Okay. Yes. After n number of crossings. Okay. Hmm.
And I think in a later figure we'll see some more details about what's the eccentricity gradient growing, and then there's that magic threshold that was again derived by Nicole years ago. So
Yeah.
we'll see
Okay.
that in the coming plot.
Time is normalized to the viscosity time scale. Okay. I'm with you. Okay. Good. Let's go back out a little bit. And I think that was the nominal model.
That's the nominal model. So there's one model I repeat over and over again and dive into great details. But then later in the paper, there's like 1,000 different simulations I do to show that these are actually quite general results.
Cool.
They
Okay.
account for a wide variety of initial conditions like ringlet mass, initial eccentricity, initial width, et cetera, a variety of viscosities. So it's a very general result.
It's robust. Okay.
Exactly.
Cool. Very nice. Okay. A little bit of detail on the initial conditions and masses here. Good. Okay. Uh,
So
about
again,
the,
that figure is just telling us the ringlet spreads until it stops spreading because eccentricity gradient has grown enough,
yep.
self-confinement has been triggered, and then the spreading has stopped.
Okay. All right. Uh, hmm. Dangerous question. Would it
Mhm.
stay flat if I ran it out 10 times longer?
So what's going to happen? Because my code is not as robust as I wish it were. If you evolve it long enough, essentially the enough noise
Yeah.
accumulates in
Yeah.
particles' motions
Yeah.
that the streamlines get a little jagged, and then eventually that noise will cause the code to crash.
Okay.
So again, I wish I could say my code was so brilliant
Perfect.
and everything was perfect that it would be stable forever. But
That's
it's not
rare.
that good. It's good
That's
enough for this
rare.
problem, so I'm very
Yes.
pleased with it. But if you push it further out, it will eventually, essentially, the accumulation of numerical errors will cause it'll cause the streamlines to get sufficiently jagged
Right.
that particles will start crossing orbits. Then they perturb each other in a crazy way, and then just the code starts
All
spitting
heck
out
breaks loose.
NANs.
But all many codes are like this. You push it hard
Yep.
enough and it will break. So,
So
very
what I try to do is I try to test the code rigorously before
mm,
breakage happens. And those are those four appendices that we're not going to go over, but all the details are in there. I very rigorously tested this code.
cool. Check it out and check out the GitHub site. Okay.
Yep.
Ooh, eccentricity is,
So this illustrates the eccentricity gradient growth that I mentioned. You
yeah.
notice we have two streamlines. So the green and blue curves show the eccentricity of the outer and the inner edges. And the outer edge, in all my simulations, when self-confinement happens, the outer edge grows eccentricity at the expense of the inner edge
Mm-hmm.
uh, until the eccentricity gradient is large enough. Then that angular momentum flux reversal that Nicole derived again decades ago,
Mm-hmm.
that kicks in, and then the ring is stable at that point.
Cool. And the mean actually decreases a
So
little.
this ringlet becomes self-confining after about 40 viscous timescales.
Uh-huh.
That tau sub nu, that's the viscous timescale. That's the timescale that the ringlet would double in size if it were simply just had viscosity and no gravity, if there's
Got
no
it.
self-confinement.
Got it. I
And
think.
those timescales are very, very short for planetary rings.
Oh yeah.
For typical rings at Saturn, it's like 10 years to double for its width to double. So the fact that we see narrow ringlets around any planets today tells us something is confining these ringlets.
So it's within 1,000 or so orbits.
Exactly.
Okay. Very cool. Very cool. I'm with you. Okay. Okay. Let's pop back out and delta W.
So because the ringlet
13.
is viscous, we also get a small gradient in the periapse, right? These ringlets are eccentric. If their periapses are co-aligned, that means they're just two nested ellipses. The
Mm-hmm.
two periapses are aligned. But when you add friction to the problem, those periapses trail one another. The outer edge trails the inner. So the orange curve
Yes.
is actually
Yes.
the difference in the longitudes of periapse over time. And that also plateaus over time. So
Mm-hmm.
not only does the eccentricity gradient grow, but the delta omega tildes grow until everything is self-confining, and then it enters a steady state.
Very cool. Very nice. Mm-hmm. Mm-hmm. Even goes down. Very cool. Okay.
And I think the next plot is going to show us
Uh,
um,
surface
the
density,
surface density evolution.
function
So
of
when there's no
fluid movement.
eccentricity gradient, essentially the surface density is the same everywhere. But as
Okay.
when you grow the eccentricity gradient, the periapses are getting closer and closer to each other, and
Okay.
their apoapses are spreading. So this is the surface density as a function of longitude relative to the periapse.
Mm-hmm.
So over time, once you get that large eccentricity gradient, this is telling us that periapse is very, very overdense compared to apoapse, where all the particles are spread far apart and the surface density is low.
Yes. Yes. There's the spread. Okay.
And this is very consistent with what the astronomers see amongst the actual narrow eccentric ringlets. They're at periapse, they're overdense by typically factors of 10 times what they see at apoapse.
Oh, okay. I didn't know that. Okay. Very cool. Okay.
And that equation 10, those are eccentricity gradients and the
Mm-hmm.
dimensionless, that omega tilde prime,
Yeah.
that's the dimensionless gradient in the periapse twist.
Yes.
And again, if you go back to Nicole's paper back in 83, she derived this nonlinear parameter Q, which is just the RMS sum of those two quantities. And
Ooh.
that's the threshold for self-confinement. And she goes through and derives when Q exceeds square root of 3 over 2, kind of an unusual number. Uh, Essentially, when that nonlinear parameter is greater than 0.87 something,
Mm-hmm.
that's when the net angular momentum flow, the orbit average angular momentum flow, is
Stops.
zero throughout. And
Stops.
if it's zero, that means there's no spreading.
Right.
So if Q exceeds that magic number, the ring wants to compact on itself. And when Q is less than that magic number, it wants to spread.
Spread.
And what I'm finding is in all my simulations that do achieve the self-confining state,
Yes.
they all settle into combinations of E prime and omega tilde prime, eccentricity gradient, and the periapse gradient,
Yes.
so that Q, the nonlinear parameter, is very close to what Nicole derived again
Very
back in the
cool.
mid 80s.
Root 3 over 2. Remember that one?
Yeah.
Of course, we should all be familiar with that from trigonometry. So, root 3 over 2. Okay. And then we get into radial profiles. Okay.
So this is also just verifying what I said earlier, that if you do a radial cut of surface density in my simulations, you're very at periapse, that's the blue box there.
Uh-huh.
You're very overdense compared to the radial cut that measures radial surface density at apoapse, which is the lower orange plot. So again, we're getting
Right.
surface density differentials, factors of 7 or so in this simulation from peri to apoapse.
Mm-hmm. Okay. Got it. Makes
And that's
sense.
just because of that periapse pinch.
Yeah, yeah. No, it
If
makes
you're if you're nearly peri-aligned, but you have a large eccentricity gradient, that means at periapse, all those streamlines get really, really close, and at apoapse, they're very, very far apart.
Gotcha. Yes, that makes sense. Very cool. Okay. And what we got next?
This is that plot of Q. So we
Oh,
saw earlier the eccentricity gradient and the periapse gradient. So there's a blue curve underneath the green curve, and I know you can't tell by eye, but there's two
mm,
curves, the blue and green are on top of each other. So blue is the eccentricity
okay.
gradient.
Okay.
Orange is that gradient in the longitude of periapses.
Mm,
Q is the RMS sum of those two quantities.
yes.
So essentially, because this particular ringlet,
W is
Q
basically zero here.
is effectively equal to E prime,
Yes.
but they rise over time as the eccentricity gradient grows. Self-gravity is pumping up the outer eccentricity at the expense of the inner eccentricity.
Yep.
They get ever closer to that magic value square root of 3/2, which is the red dash or dotted curve.
Mm-hmm.
That's the value Nicole said. That's when angular momentum flux
Saturation.
reversal is complete.
Like
There's no
saturation.
net motion of angular momentum radially inwards or outwards.
Mm-hmm.
And when that happens in my simulations, that's when the ringlet stops spreading. So everything's very consistent with what Nicole predicted, again, back in the mid 80s. So I feel this problem was effectively solved in the 80s. One of what Nicole didn't really look at the time is she's focused on viscous ringlets. And she showed if you had sufficient eccentricity gradient, your ringlet can be self-confining. What I found in these simulations is even if you don't have an eccentricity gradient, if you
Okay.
just have an initial eccentricity, self-gravity will cause your eccentricity gradient to grow
Bro.
until you hit that magic square root 3/2 value. So
Mm-hmm.
it's a very robust result.
Very
If you have
cool.
more mass, I believe, in the ringlet, I think your eccentricity grows faster, which means it hurries you up towards that square root 3/2 threshold. If you
Yes.
have less mass, that means you spread more before you hit that threshold, but eventually you hit it.
Yeah, right. Okay. Mm-hmm. Mm-hmm.
The interesting state, or the if you imagine a ringlet that had no initial eccentricity,
Okay.
what,
Circular.
even if you're gravitating, because you have no eccentricity, essentially you have two circles perturbing each other, and they'll
Yep.
always stay circled. So you'll never grow your eccentricity gradient if you have a zero eccentricity. All you need is a modest non-zero eccentricity. So that's actually a key ingredient for any of this to work.
Mm-hmm. Mm-hmm. And of
And
course,
we'll discuss it more when we come back to the origin of narrow eccentric ringlets.
okay. Yeah. Oh,
And the
yeah.
one I throw out there in the paper is admittedly a bit of a fairy tale. It's a bit of a stretch,
It's okay.
but it's the best fairy tale I can come up with.
Oh, I love
So
fairy tales. So very good.
hopefully we'll have time for that.
Okay. I'm with you. But of course, zero eccentricity is sort of a singularity in some sense, right? Almost nothing has exactly zero. So
It's
very
much
cool.
easier to have a very small but non-zero
Exactly. And
eccentricity,
then it grows and then it will do its thing.
right?
So very
But
cool.
if your initial eccentricity is small, that means essentially these are secular gravitational perturbations, which tend
Uh-huh.
to scale with the perturber's eccentricity.
Yes.
So if your initial eccentricity is very small,
It takes.
it'll take a long time for you to develop that eccentricity gradient, which means now your narrow ring is probably pretty wide, pretty not narrow.
Okay. Cool.
So mass helps, large initial eccentricity helps, but again, the results are pretty robust, even if you have less mass, less viscosity, less eccentricity, you'll
Very
still drive towards the self-confinement state.
beautiful. 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 Okay. Let's roll on and we get into the angular momentum and energy fluxes and luminosities.
Yep.
And we have some expressions here for viscous transports and all.
And most of this is coming from out of, Fluid Dynamics 101.
Yep.
So my code is n-body integrator, but to compute the ring's viscous forces, I reach out for fluid dynamics, right? I'm not simulating the actual physical collisions between centimeter-sized ice particles, the
Right.
bajillion of those that actually exist in Saturn's rings,
Hmm.
I have to use approximate methods. So rings behave like viscous fluids, or at least so the community thinks.
Yes.
So that's where all these equations are coming from. It's fluid dynamics for viscous fluids, but I'm taking those formulas and applying them into my n-body code. So the code itself is a bit of a hybrid. It's an n-body integrator, but I rely on fluid dynamics to figure out
Yes.
what the forces are as these streamlines, which are really they're little sliding arcs that slide past each other.
Yeah.
They're sliding each other. They have frictional forces. That's how I compute the viscous forces as they slide past each other.
Cool.
So a lot of these equations and plots you see, that's mostly me confirming I'm getting the physics right.
Cool. And angular shear, DWDR. Okay.
So if the ringlet were circular,
Yes.
again, so we have two streamlines, if everything's circular, we know what the angular shear is. It's just the radial gradient and the angular velocity. So in natural units, that's -3/2 or -1.5.
Hmm.
So again, this is my nominal simulation at various times, late, early on versus late. So initially, everything is, the two streamlines, they're eccentric, but there's no eccentricity gradient.
Right.
So the angular shear is very close to the minus, 1.5 value, again, in
Hmm.
typical nominal units. But
Hmm.
as that eccentricity gradient grows, you'll notice at periapse, which is at the center of the curve,
And
the angular shear gets smaller and smaller until it passes zero as we
yes.
go from orange, green, and red. If you
Yeah.
look at the legend, the eccentricity gradient of the ringlet is growing, again, because of the self-gravity, pumping up the
Mm.
outer eccentricity at the expense of the inner.
Um,
And eventually the angular shear reverses at periapse. So if your ring particle is traveling around that ellipse at apo, your angular shear is negative, but at peri, your angular shear is positive. So
Guys.
what that means is the flow of
Yes.
particles near you is reversed. So now you're handing off angular momentum in the opposite direction. Angular momentum is flowing inwards at periapse and outwards at apoapse.
Oh, that's wild.
And if your eccentricity gradient grows strong enough, and that's what you see at that, I think it's the purple curve there, the top curve.
1.8, which is really eccentric. Wow, wow.
Yep. So that's where we've just crossed that square root 3/2 value, which
Hmm.
I think is 0.877. In this simulation, it's 0.88, so we're very close.
Good.
What I find is the ring has the orbit average angular momentum luminosity, right? It's the flux integrated around the ellipse, has zeroed out. It's not negative everywhere. It's not positive everywhere. It's very close to zero. And that's when you're in the self-confining state.
Mhm.
So in an orbit average sense, the ringlets don't want to evolve away from each other or towards each other.
Okay. Want to say
And
something here
these
about
plots are just confirming that storyline.
yeah, you want to say what equation B11 is here?
So that's just if you take the formulas from Nicole, she derived all this again in those 80s.
Good.
If you plug in I can't remember if I think I used square root 3/2 for the eccentricity gradient. That dashed line is what Nicole said it should look like.
Very cool. Good comparison. Very nice. Validation, verification, actually. Okay. Yay, Nicole. Okay. Very nice. I like that figure. Okay.
And those 1, 2s, and 3s states, again, this is me just looking at her paper, and she showed that if your eccentricity gradient is below some threshold, everything is just going to spread away from each other. So it's a viscous ring that's going to want to spread. You won't get sharp edges. She also pointed out that if your eccentricity gradient is between 0.75 and that magic value, √3/2,
Okay.
then angular momentum flux is getting reversed at periapse, but it's not complete. You
Yes.
still got a net radial angular momentum luminosity that's positive. So the angular momentum luminosity is lessened, but still positive, and spreading occurs. It's
Huh.
not until you either hit that √3/2 or go beyond. If
Huh.
you're at 3/2, square root 3/2, the orbit average angular momentum luminosity is precisely zero. The ring is in a steady state. If you go beyond that, your actually angular momentum is going to flow inwards, which is going to cause the ringlet to get more radially concentrated.
Correct.
So the magic threshold really is √3/2. And
Wow.
I see that in my simulations, but if you look closely in my plots, it's not exactly √3/2. It's very close though.
Well,
I'm getting, confinement, self-confinement happens at 0.88
Yeah, that's what we
instead of
thought. Yeah.
0.866 that
Mhm.
was predicted by Nicole. And I'll have an explanation for that in one of my plots.
Close. Very close. Okay. Thank you for going over this. Very nice. Okay. You get gravitational transport. And here is the angular momentum flux.
Yep. And that's telling the same story. It looks similar to the other plots about the previous plot was about, angular shear. But again, when the shear changes sign, you get the angular momentum flux is reversed. So that's the
Yep.
blue curve is angular momentum flowing outward at the initial state where there's no eccentricity gradient. So you get very vigorous outward flow of angular momentum. The ringlet spreads radially very fast.
Yes.
But as you dial up the eccentricity gradient, you get that flux reversal, meaning the sign changes
Beautiful.
essentially at the pink curve there. So there, the eccentricity gradient is 0.788. So
0.788.
you're getting positive angular momentum. I'm sorry, you're getting negative viscous angular momentum flux. So angular momentum flux is flowing
Correct.
inwards, but only at periapse. It's still going outwards, but at a reduced rate at other longitudes. But as you dial up that eccentricity gradient a little bit more,
Doom, doom,
if you
doom,
look at the
doom.
yellow curve, eccentricity gradient is now 0.878. And there, the orbit average of that yellow curve is very close to zero. And that's when the ringlet is
Yes.
self-confining, it's in a steady state, and it has sharp
Sharp
edges.
edges.
We'll come to those sharp edges in later plots.
Very cool. Okay.
And the following plot is just the integral of those other curves you saw earlier.
Oh,
So if you integrate over longitude,
yeah, yeah.
the blue curve shows the viscous angular momentum
Integrate those.
luminosity
A
uh, trending towards very close to zero, not exactly zero,
little bit above.
but the orange curve shows the gravitational luminosity. So angular momentum luminosity due to self-gravity, right? These
Yeah.
streamlines have gravity; they're all pulling on each other, and that communicates angular momentum. And you notice that's always negative in these simulations.
Yes.
And it turns out my ringlets enter the steady state when the positive, slightly positive viscous angular momentum luminosity, the blue curve, precisely counterbalances
This
the
light.
negative gravitational luminosity.
Mm-hmm. Mm-hmm.
That's when my ringlets enter the steady state. And that's the main distinction between what Nicole reported earlier. She was mostly studying viscous but non-gravitating ringlets. There's a caveat there. She has other papers where she does both, but she's mostly looking at librations,
Okay.
oscillation of ringlets.
Yeah, yeah.
Here, we're looking at the similar ringlets, but we're allowing them to spread radially due to viscosity. But again, if self-gravity pumps up the eccentricity gradient, all those angular momentum luminosities conspire to zero, and that's when you enter the self-confining state.
Cool. That's neat. Okay. On 10, now let's
And
see.
here we're just zooming into the right end of that curve.
Yeah,
So
I was
again,
gonna
blue
say
curve is,
it's right down
yep,
in here.
yep.
Okay, so we're gonna zoom in on that one. Okay.
So blue is the viscous luminosity.
Ah, thank you. Good.
Orange is the self-gravity luminosity,
Mm-hmm.
and the green is the sum of those two. And you notice they're dancing around zero. So in a time average sense, it's zero.
Zero.
If you notice those wiggles ramping up
Yes.
in those curves,
Yes.
this I think is a symptom of the
Yes.
numerical instability
Yes.
that I
Yes. Yeah,
suspect
you were talking
exists.
about earlier. Yeah, yeah.
Right. So if I push these curves out far enough time, the oscillations will get more and more
Bro.
vigorous.
Yes.
What's happening is the streamlines are getting more and more disturbed. I think it's just the accumulation of numerical errors over time.
Mm-hmm. Mm-hmm. Mm-hmm.
And eventually things will just crash.
Yeah,
But
it eventually is.
the
Uh,
good news is, until then, angular momentum is conserved. I have some plots that check that for this simulation.
okay.
The quick spot check is angular momentum conserved? Because it should be, even when you have
See.
viscosity.
Yep.
Angular momentum is always conserved. And I think there's a plot in the paper somewhere that shows it's conserved.
What is the okay, one, two. Oh, these are the purple, the horizontal lines are a mean or something?
Yeah, it's just me adding lines to guide your eye.
Got it. Okay. Got it. They do a good job of that. They caught my attention.
Mhm.
All righty. And viscous flux, angular momentum.
So there's viscosity, there's gravity. So from those forces, we can compute angular momentum fluxes.
Yes.
And this just shows how those curves vary around the longitude of the ring. So periapse is in the middle, um,
A little bit.
apoapse is at the edges. And again, if you mentally integrate both curves, you'll get for viscosity, you'll get a positive non-zero value.
Yes.
And likewise, for gravity, you get a negative non-zero value, and those
Uh-huh.
two values sum to zero. But this just shows how those two quantities vary with longitude.
Mhm.
So essentially, if you're only concerned about viscous angular momentum, whether it's flowing radially or not, it's only flowing inwards. This plot is telling you it's flowing inwards at periapse, where it's very negative, and
Mhm.
it's lightly positive. It's essentially flowing radially outwards at apoapse.
Yes. Okay.
So it's symmetric around periapse, whereas gravity is different. Their gravity is sensitive to that misalignment in the periapses. So one edge of the ringlet, if your ring particles that are approaching periapse, that's the left half of the orange curve,
Okay. Yes.
you are losing angular momentum to the outer streamline as
Ah,
you
that's the
approach
transfer
periapse.
part. Okay.
But,
Okay.
but then that flips after you pass periapse. And that's mostly due to the misalignment, the small misalignment in the periapses. And that is a consequence of just the viscous friction in there. When you add friction,
Yeah.
those streamlines are going to get misaligned slightly.
Okay. Okay.
That goes away. If you were to turn down viscosity, that misalignment would go to zero, and then the gravitational fluxes and luminosities would all just go to zero.
Yes. Yes. Okay. Good. Good. We hit an expected limit. Yay. Okay. Energy flux.
So not only do we have a flux of viscosity, I'm sorry, of angular momentum,
Mhm.
because we have frictional forces here and gravitational forces, the streamlines are trading energy as well, orbital energy. And again, so this is just computing those fluxes. And
Good.
then if you mentally, integrate around those curves, I
Yes.
think that'll get us to the luminosities, which are the orbital sums of those fluxes. And again, those curves are going to trend to zero as the
Yep.
ringlet enters the self-confining state. So not only is there no, when you enter self-confinement, not only is there no net, orbit average angular momentum going from one streamline to the other, there's no net orbital energy. It's because all those fluxes conspire, they sum to zero in the orbit average sense.
Good. Good. Very
So this is
cool.
another spot check on, is the ringlet stable?
Yes. Yes. Very cool. Okay, variations in mass. Oh, here's our grid of simulations
Mhm.
done.
So all the
502.
all the simulations I showed you earlier were for that one nominal ringlet.
Yes.
I've since varied the initial width. That's the delta A's you see above each chart.
Hmm. Hmm.
And the x-axis is variations with ringlet mass, ringlet viscosity. So when I do this grid survey, the color dots tell you when the simulations settle into self-confinement.
Okay.
And the X's tell you either it didn't self-confine or the code crashed.
Okay.
And the reason the code might crash, actually, it gives up. What happens in my simulation? I just have a linear treatment of viscosity, but you can imagine in a real ring where streamlines get really, really close to each other,
You may pick
you can imagine particles are banging into each other, creating shocks,
Uh-huh.
and all that physics is not in my code. My code is just simple linear hydrodynamics.
Mm-hmm.
Uh, Streamlines get too close, particles are piling up on each other. That's not modeled here. So in the code, when they get too close, the streamlines cross, and when the code detects that, it just gives up. So all those X's are where stuff got too close to other stuff, and the code give up.
Okay.
That doesn't mean self-confinement can't happen. It just means I need more physical, more realistic
Right. More
treatment
physics
of
in that.
exactly
Okay.
shocks. Particles can pile up in the vertical sense, and none of that is in here.
Okay. Good. Let's see. Boop, do, 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 d greater than 0.8.
And the color coding is kind of interesting.
Yeah.
The deep blue are results for ringlets that behave like the nominal model. Their eccentricity gradient got very large,
Yep.
came very close to that root 3/2 value.
Yep.
But for some simulations, what I find is that the eccentricity gradient peaks, it plateaus at a smaller value, and instead that periapse twist, the delta omega tilde, gets
Yeah.
large. So remember the nonlinear parameter that Nicole derived has
Uh-huh.
two components. One is
Uh-huh.
eccentricity gradient, and the other is periapse twist.
Yes.
So in the green and the yellow, those are simulations where the periapse twist is the larger contributor to the
Stronger.
nonlinear linearity pattern.
Oh, cool. Oh, and I
And
just,
that's also very relevant to observations of ringlets because
yes.
all observed narrow-centric ringlets, they don't have these large eccentricity gradients. Some of them have eccentricity gradients of zero point 0.3 or zero point 0.4, zero point 0.6. I think zero point 0.6, maybe zero point 0.7 is the largest that I'm aware of.
Okay.
None of them hit that magic √3/2, which is 0.877.
Which tells me something.
Um, so what that means is if these simulations apply to the observed ringlets,
Yes.
they have to have large periapse twists.
Yes. Yes.
So I'm okay at Saturn because we either have very few or no measurements of periapse twists. It's actually hard to observe that either,
Oh, I
using
know.
Hubble or James Webb or even with an orbiter like Cassini. I'm unaware of any tight measurements on the periapse twist of Saturn's ringlets.
Right.
That does not apply at Uranus because there, that very oblique planet is presenting a face-on view.
Right.
And Dick French, I think just within the last year, published a paper where he measured both. He measured E prime and omega tilde prime
Cool.
for the 10 or so narrow ringlets there. So when you look at his chart, his table of numbers, you do the RMS sum. For Uranus, I'm not getting Qs of close to zero point 0.9.
Okay.
Instead, they're essentially dominated by their eccentricity gradients, so
Okay.
they're coming at zero point 0.5 or zero point 0.6 or less.
Uh-huh.
So either the Uranian ringlets are not like the Saturnian ringlets, or my model only applies at one planet and not the other.
Eh,
My model doesn't apply to any
any
planet.
of
So
it.
it's a little concerning. So things were look promising so far, and then my good buddy Dick French published that paper that is kind of blowing a hole in this work, but
Popped a
it's
hole.
still an interesting challenge.
Progress is good. And for those who are wondering, here's the nominal case right here. I assume that's what the N means.
Yep.
Yep. Just so you see where it fits in the topography of the model study. Okay. All right, we got lots of things to do in the future. We'll come to that. Okay, let's see where we go. Yeah, this is the growth of the eccentricity gradient. And ooh, here's some observations. Maxwell, Titan, Laplace, and Huygens.
So those are ringlets. These are the well-studied ringlets at Saturn.
Mhm.
So these observations are mostly coming from Cassini. So Cassini, as well as prior to Cassini, we had good observations of the eccentricity gradient of Maxwell, Titan, and Laplace, and Huygens is there as well. Huygens has effectively no eccentricity gradient.
Mm-hmm.
And then the sea of curves you see are a subset of the simulations that were pulled from that survey I did on the previous plot.
Right.
So the goal was to see, do the known ringlets have eccentricity gradients that are comparable to what I see in my simulations? So
Mm-hmm.
what's interesting here is I have a spread of eccentricity gradients that kind of overlaps Maxwell, Titan, and Laplace. I
Yes.
don't have any I don't have any simulations of self-confining ringlets where the eccentricity gradient is, of order 0.01. So there's a
Okay.
gap between my simulations and Huygens.
Uh-huh. Uh-huh.
So this could be telling us Huygens is not like the others. And if you look at the Cassini images of Huygens is very complex. It has lots of structure,
Yes.
whereas most of the other ringlets you see here, they're fairly smooth. They look like a classical, narrow eccentric planetary ringlet.
Or streamlined.
So maybe the discrepancy is because Huygens is just some completely other beast.
Could be.
Maybe there's a discrepancy. Maybe the model doesn't apply. Maybe it doesn't apply to all these. Um, but anyway, I'm at least pleased that 3 out of the 4 well-studied ringlets are consistent with
This
what I see in my
scenario.
simulation.
Uh-huh. Uh-huh. Very nice. I like that one. Let me take that one instead. 15, 16. Okay. And then we got some eccentricity damping going on. And periapse twist. Bouncing around.
So the next few figures are me just convincing myself that this is a robust result. What happens when you play with viscosity?
Right. Right.
Well,
Exactly.
as you might imagine, you add more friction, the periapses get more misaligned, and that's what these curves are showing.
Yes.
You still get the self-confining states. All those curves are trending. They're flatlining, sort of. There's still some wiggles, but
Little ones.
the story is consistent. Dial the viscosity, you get more
Right.
periapse twist, but they still enter the self-confining state.
That makes sense. Okay, good. That's a nice sensitivity study to do. Good. Okay. And seven ringlets.
Eccentricities. So like I said earlier, if you have larger eccentricities, that's the purple curve. My nominal curve, my nominal ringlet had the eccentricity in the middle, 0.01. That I think is the
Okay.
purple curve in the middle.
Curve right
So
here.
as you dial up the
Ah,
eccentricity,
yeah,
the initial eccentricity, that allows self-gravity to more swiftly grow the eccentricity gradient.
yeah.
So you more swiftly enter the self-confining state.
Right. You
If
can
your
see that
initial
here.
eccentricity is lower,
Takes longer.
it takes longer, exactly.
Mhm.
And the blue curve is what happens when your initial eccentricity is
Everything
precisely
is.
zero. There you spread forever.
Yep. Yep. Very cool. Good. Yes. 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 It's all hanging together. It's all hanging together. Okay.
It hangs together in the paper, but I'm still worried about those Uranian ringlets.
Yes. We'll come back to that.
We have E prime and omega tilde prime measured. For all those ringlets, their nonlinear parameter is significantly less than that magic
Root
root
3 over 2.
3/2.
Uh-huh.
So I think that means I'm not dead in the water. I think there's more out there. There's more physics. There's more to the puzzle.
Good. Good. It's always good to have a little mystery. Okay, and this is eccentricity is
So
focused on relative to
this
the
is
state,
this
right?
is the ringlet's mean eccentricity. So
Okay.
there's an eccentricity gradient, but if you just average both the eccentricities of both streamlines,
Mm-hmm.
what's happening is they're decaying. So not only is self-gravity pumping up the eccentricity gradient, if you evolve for longer periods of time, what's happening is you have friction in the ringlet, so you have energy losses. If you have energy losses, um,
He's going to go down.
energy is being radiated. Collisions are occurring. Uh, ring particles are getting a little warm. They're radiating energy into space. So what
Yes.
that causes is the semi-major axis of the ringlet to shrink over time. It's
Yes.
really, really tiny. It's a slow process. It's weak, it's tiny, but it's significant
Mm.
because if your remember angular momentum is conserved. So
Yes.
if your semi-major axis is shrinking, the angular momentum is root semi-major axis times quantity 1 minus e squared.
Yes.
So if E is shrinking, E also has to shrink.
Yes.
And you can derive the rates at which these are shrinking.
Cool.
So this is another consistency check. I just use the relevant physics. They tell me all my simulations, when I plot it in these units, their mean eccentricities of these ringlets should shrink as indicated by the dashed line. So
Yes.
all the other codes are from a variety of simulations. They all kind of closely track not at precisely the same rate, but they're all going down at
Very
comparable rates.
close. Very
This is
cool.
a nice confirmation check, but
Yes.
it's also a little concerning because if you think about it, if right, they have to have an eccentricity gradient,
Yes.
but their eccentricities are shrinking.
Mean.
So eventually, if you turn the crank long enough, the inner edge is going to circularize first.
Right.
And
Okay.
that means, well, now since the outer edge is also losing eccentricity, now our eccentricity gradient is getting below that magic value.
Yes.
If you extend this curve way to the right,
Oh, yeah, 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 yeah.
you're going to leave the self-confining state. So this plot is also telling me self-confinement via this mechanism it's temporary. It has a discrete lifetime, and in the paper I calculate that lifetime. If you
Yes.
scroll down, I think we'll see
Think of a 1,000 year-ish kind of thing. Time
it's
scale.
like a million orbits. So it
Okay.
seems like a large number of orbits. In fact, there it is in the text. For the nominal ringlet, if you scroll up a little bit, it's a million orbits. But the orbit of a planetary ring particle at Saturn is only 5 or 10 hours. So we're talking 1,000 years. So
Okay.
self-confinement, as seen in the simulation, sounds wonderful, but it's temporary and it's still really, really brief.
Huh.
So the main lesson here is ringlets can evolve into the self-confining state. So it seems to solve the spreading problem, the short timescale spreading problem,
Right.
but it
But
doesn't solve it forever. It just merely extends it for, it multiplies instead of ringlets having a viscous timescale that's only of order 10 years, it actually has a self-confinement timescale that's of order,
Down.
a thousand, tens of thousands of years.
Okay.
So I've extended the lifetime problem for, I think in the text by a factor of 3,000,
Mm-hmm.
but still really, really short compared to, the age of what we think planets and their rings are. So it's still a problem.
Mystery, mystery, mystery.
There's more to the puzzle.
Ah, and yes, we did do two streamlines. What if we crank up that number?
Exactly. And
Mm-hmm.
this plot and the next plot mostly show that, as you dial up the number of streamlines, essentially the self-confining state is achieved. You just have more particles doing the desired dance.
Mm-hmm. Mm-hmm. Mm-hmm.
And I think
Good.
the next plots show the same for the periapse.
Periapse. Yes. Yep, there's our two. And then for those who question, well, what if I have 14? There you go.
I wish I could say I could do this for thousands of streamlines, but then the particles get so tightly packed, they very quickly perturb each other and scatter, and that causes the code to crash.
Right.
So
And
again,
that's physics is not
this
in
is one of the limits of the code. If you throw enough particles in there, you would think that with more fine-grained simulations you could do more, but no,
good
it
point.
gets
But if
too
you don't have the
busy.
physics in there,
Exactly.
very
So
cool.
the code is good enough as long as the number of streamlines is small.
Hmm.
But if you want to do lots and lots of streamlines, reach for one of those higher powered n-body codes that can do millions of particles.
Uh-huh. And then do a pull request on GitHub once you get all that in
Exactly.
there. Very good. 21, 22 surface density profiles, periapse, as a function of the number of streamlines. Okay.
Mhm. So here, as I dial up the number of streamlines, and again, my range goes from 2 streamlines to 14. I
Mm-hmm.
can't go much beyond 14, or else the
It
the
never gets out
streamlines
of the
are
box.
too busy and they collide and the code complains. But anyway, as I slowly dial up the number of streamlines, I do indeed get sharp edges as expected. So with two
Yes.
streamline, everything is sharp, and that's just an artifact of having two streamlines. But
Well,
as you go
there
to
you go.
8, 11, 14,
Still short.
um, it stays sharp. So this is one of the reasons I have some, partial faith in these results. We see sharp edges, they're hard to explain, and the code reproduces that, which is why I think angular momentum flux reversal is playing a key role in
Yes.
maintaining the sharp
Must.
edges.
Must.
But the main discrepancies between these results and what the astronomers see is, uh, like at Uranus, the square root e prime plus omega tilde prime is not square root 3/2, which is concerning. And I had another one in my back pocket, and I'm drawing a blank. But if it pops in my head, I'll come to it.
Okay, how about Neptune? Do we know
So
anything?
yeah. Oh, so there you have arcs of material. I wouldn't
Yes.
throw this code at ring arcs
Okay.
without some major adaptation. So it might be doable,
Okay.
but
Okay.
this code out of box won't do Neptunian ring arcs.
Okay. Cool. And then final plot, I think, in the
And
paper.
this is the counterpart to the previous plot. The previous plot shows surface density along a radial cut at periapse, where the
Yes.
ring is very tightly, because that periapse pinch, all the particles are close to each other.
Mm-hmm.
But if you do that at apoapse, you notice the radial scale is changing dramatically. At apoapse,
Oh,
the ring particles, the
yeah, yeah,
streamlines are spread out by factors of
yeah.
10 or so,
So
but
this
you
is
still get sharp edges at periapse and
yeah
apoapse.
at the outer edge. Uh-huh. Uh-huh. Very nice. This one converges a little better. Okay. Very cool. Beautiful. Beautiful. And we're gonna how about origin? You want to talk a little bit about origin?
Sure, this is that
Want to
fairy tale I
speculate? You
mentioned
want to
earlier.
speculate?
So we have a nice confinement mechanism, gives you the sharp edges. It is temporary, which is concerning. Um, of course, now, you know, in the Cassini era and post-Cassini era, there's lots of other studies that say rings are young. They're not ancient like the planet, right?
Oh
Planets are
yeah.
4.5 million years old.
Right.
Maybe the rings are young. So there's numerous works out there that say, Saturn's main rings might be 100 million years old.
Right.
My ringlets have to be really, really young in order to be
Baby one.
self-confining. And I'm only getting, self-confinement episodes that are of order 1,000 years. So maybe if this scenario applies to the observed suite of narrow ringlets,
Okay.
uh, not only are they young, but they have to reproduce themselves. They have to, right? If they're young, they'd be gone in a flash. But what if the main rings are spawning off young
Ah,
ringlets?
right.
And
Okay.
the clue, the seed for this fairy tale was a paper by it's in a 2001 paper by Poulet and Sicardi. I thought it was a great paper when I read
Yeah.
this.
Right
They
here.
were looking at at the the shepherd satellites for the F ring. So that's
Yes.
Prometheus and Pandora. They
Uh-huh.
they are shepherd. They straddle the F ring, which is
Yes.
just exterior to the outer part of the A ring.
Mm-hmm.
But we also know that again from calculations that Peter Goldreich did back in the 80s,
Yes.
that if you have a perturber near a disk of material, and he was considering, planets orbiting in disks as well as rings at the
Yes.
time,
Uh-huh.
um, satellites orbiting near rings, you have resonances in those rings.
Okay.
Your gravitational perturbations at those resonances tend to launch spiral density waves.
Yes.
Those waves propagate away, but they carry angular momentum. So for a satellite that's orbiting exterior to a ring, a main ring, you have many resonances, you launch many waves, you're sucking angular momentum out of the ring. Your orbit is going to expand outwards. And they derive this. This is type 1 planet migration, by the way, that's widely used in planet formation studies.
Yes.
But again, it was all derived by Peter Goldreich, Scott Tremaine,
80s.
late 70s, early 80s.
Mm-hmm.
But it was Poulet and Sicardi who applied those formulas to
Ring.
to Prometheus and Pandora, and they showed if you work the clock backwards,
Yes.
that because of the torques they're exerting on the ring, if you go backwards in time, they had to have emerged from the main ring about
Yeah.
20 million years ago, I think is the number.
Yeah.
And if you turn the clock forwards, they're also going to show those two satellites because the inner one is the more massive one. It's migrating outwards faster because it experiences the bigger torque from the closer A ring. So it's creeping up
Right.
on the smaller one, and they're going to collide in about 20 million years.
Mm.
So if two satellites collide, if they can collide with enough vigor, they can smash each other to bits. That's the seed for a
There's a
narrow-centric
ring.
planetary ringlet.
There's a ring.
Maybe. It's a complicated fairy tale, but it's the one I'm going with.
Stay with it until proven otherwise.
Exactly.
Very cool.
So that's how I claim to solve the narrow ringlet age problem. It doesn't really solve it. It just means if this works, the main rings are spawning, satellites
Yeah.
fairly regularly, and the innermost big one always, it migrates faster than any smaller neighbors outwards. They're eventually going to collide. Here's
Bang.
another if, I have a daisy chain of if statements. If they collide vigorously enough, they'll smash each other to bits and form another narrow-centric planetary
Never
ringlet,
knew it.
which
Oh,
will
I love
settle
that.
in the self-confinement state,
I love that.
or so I claim.
Very cool. Well, we're going to hang on to the future here in a little bit. But there are some really awesome appendices in here, people. I encourage you to check out the really dry but very important technical stuff. So do check that out. And Joe, I want to thank you so much for walking us through this very lovely article. Thank you.
Thank you for having me. I enjoyed talking about this lovely article.
Yeah.
Okay.
And you hinted at it a couple of times, and it was certainly there toward the last section of the paper. And so let me just push and ask, where do you think we go from here, given the published article? Maybe both in terms of the fairy tale, improving that, expanding out to other rings, Uranus, for example, Neptune, etc. And observationally, maybe where do we go to test additional aspects of this? So future directions. Where do we do next?
Future tests might be to, can one observe Prometheus and Pandora creeping outward? They're the biggest perturbers near the rings.
Okay.
These are the F ring shepherds.
Yes.
I'd be very interested if someone could use what observations we have today, which go back decades. There's Cassini, obviously, but people have been monitoring satellites using HST. Now they're doing it with James Webb.
Yep.
So if that baseline of observations gets long enough, can we see the gravitational torques that the rings might be exerting on those
Yeah.
satellites?
Yeah.
And that might make my case that, rings are spawning off satellites small satellites, and if they can merge instead of spread away from each other, they can possibly form ringlets that way.
Hmm.
You have other effects competing with gravitational torque from the rings. There's, the tide from the planet itself. So
Ooh, yes,
uh,
right. Hmm.
if I were to push on this further, I would go back and check, tidal rates versus gravitational torques from the satellite,
Okay.
and then see maybe we can, if there's a long enough observing baseline, or if a new campaign could spot that. Um, Keep trying to measure those omega tildes, the periaps
Yes.
uh, twist, or
See if we can get
periaps
that.
separation between outer and inner edge.
We can get a cue.
If they can be measurable, if they're big enough to be observed at Saturn, they scale with viscosity. So that might be a nice way to infer the viscosity of ringlets, which is also essentially how much friction there is due to collisions among ring particles. That would be nice to have. And then there's other applications of the code that have nothing to do with rings. They're spelled out in the paper. That section of the paper is really my marketing section. I would love to apply this code to maybe galaxies, or planet forming environments. They all
Whoa.
disk, galactic disks rather,
Yeah, yeah,
or
yeah.
planet forming environments.
Uh-huh.
Um, I don't know enough about, either to take the lead on that. So this is my appeal to future collaborators who might want to download the code, play with it in whatever environment that's of interest
Prove
to
it.
them, whether planet formation, evolution of galactic disks, and see if we can collaborate and work together and solve some other interesting problem.
Very cool. Very good. Go for it, people. Engage
Please
it.
do.
All right.
And I'm a soft money research scientist, so please add me to your proposals.
There you
I
go.
promise to be a small line in your big budget.
There you go. You're a
I
cheap
should point
tourist.
out,
You're a
my
cheap
day
tourist.
job, my day job is in the private sector. I work for Oracle by day,
Yes.
but I moonlight as a research scientist. So I would like to collaborate with more of my colleagues and future peers who can help me, tag along with efforts, apply the code to these new environments that I think where the code is applicable.
Cool.
And if you can pencil me into your budget, add me to your phase one, let's talk.
That would be great. There you go, people. Do it.
Super.
Joe, thank you so much for walking us through
Thank
your
you,
very
sir.
awesome article. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you in the next one. Bye bye.
Yeah, see ya.